Hi, everybody, welcome back. Eric here from the Right Click Save project, and this is reading the F and docs of the Solidity language. We are still in the basic section. Today, we're going over the Ethereum virtual machine, or the EVM. And once again, we're not really going to go through any code. This is just setting the foundation for what we need to know as smart contract developers. So what is the EVM? It is basically, like it says here, the runtime environment for smart contracts. And it's actually a very complicated thing. We're only going over a handful of concepts today, so let's get started. Number one is accounts. Basically, there's two kind of accounts. That is external and contract. They're treated the same by the EVM, but they are created differently. And with external accounts the address is created by your public and private keys, whereas the contract accounts are created by the creator's address as well as the nonce. And they can both have storage, or they both do have storage associated with them. Storage is basically key value pairs, and they each can have a balance associated with them. And that's it for accounts. Let's move on to transactions. Now, a transaction is going to have essentially three parts, which is an amount. So it can have a certain amount of ether associated with it. It can have some data associated with it, and it can have a target associated with it. And the data is called the payload. And these transactions can essentially, like we said before in a previous video, they are the records in our record book, essentially. They can send data, they can send money, they can create a new contract, and this is all based on the inputs and how they're organized. And now, moving along, we're on to gas, the almighty gas. So just like your car, you need gas. Can't do anything without it. Gas is how the blockchain works. This is what incentivizes the miners in order to keep this whole thing operational. So basically, every time you send a contract, you need to send, every time you send a transaction, you need to send a certain amount of gas with it. This is calculated by just how complex the the computations are going to be. We'll get into that a little bit more later. And that's pretty much it. You want to send a little bit of extra gas to incentivize the miners to actually pick up your transaction, and any difference that is not used is sent back to you. Here we go. Storage, memory, and the stack. Now, this is probably the element that we're going to concern ourselves most with out of all of these, as we're running our smart contracts. Basically, this is where we store our data. So there's three things that we're going over here. First one is storage. Storage is what we think about when we write to the blockchain. So if we go back to our example here, and one of our sample contracts, one was coin. This variable here, balances, is a mapping. This is in storage. So for instance, if somebody wants to add an address that will map to a uint, if we can add more, we can update balances, and we can read balances. This is all going to be persisted on the blockchain itself. However, this is actually the most expensive way in terms of gas to create data and have it stored on the blockchain. So if possible, when you can, you want to try to use other means of storage. So for instance, memory in the stack. Now, memory, if you come from another programming language, you can think of memory as so temporary space. So for example, if you have a local variable inside of a function, once that function completes, that variable is wiped out and garbage collected. So, it's the same concept here in Solidity as memory. Storage, like I said, kind of works as like a key value pair. Memory works more like an array. So one thing to keep in mind is, how you manipulate the memory. And one more thing called the stack. Now, the EVM is what they call a stack machine, as in instructions and everything else, they're pushed onto a stack and popped off as need be. The only problem with a stack, if you remember your data structures, is you can only take the top element. Now in EVM, there's some little extra rules here. It's slightly more complicated, just pushing and popping. But the point is, it can be cumbersome to manipulate if that data structure doesn't fit what you're trying to do. So one more thing to keep in mind as you're using the stack for memory location. There's another place called, for your data input that's going to come with a little bit of memory. So for example, a parameter that you use to pass into a function. So sometimes a little trick that developers use is they use that for a piece of memory. Again, this all depends on your application. So let's move on. Next part here is instruction set. So basically, I have a list of opcodes. There's a look over here. So our smart contracts that we write will actually compile down to another language, lower level, called this. We're calling it inline assembly language, and those are, here's the documentation for that. We have a add function, a subtract function, multiply function. So these are actually, when we talk about computing gas earlier on, what that is doing is adding up the opcodes that your smart contract will compile down to, and each one of these will have an associated amount of gas required to run that. So that's basically what we're talking about with this instruction set. And if one more thing is that you can also manipulate these directly via your smart contract. So optionally, if you want, and if you know what you're doing from your smart contract, there are ways that you can actually write inline assembly on your own. So perhaps maybe the Solidity language doesn't support something that you want to do. You can do it. You can always do it yourself in assembly. But again, make sure you know what you're doing, because that can lead to some pretty unforeseen situations. Message calls. Message calls is how contracts can speak to each other, send ether, call a function. But wait a minute, I thought that was a transaction. Okay, so I think the main thing here to keep in mind is that messages and transactions are two separate things. They're very similar, but separate. One way I like to think about it are transactions are slightly higher level and messages are a little lower level. Transactions are how you interact with the blockchain, and then messages are how contracts interact with each other. Transactions often contain messages, and that's pretty much it. There's actually more to to deal with here. One thing to keep in mind as you send messages, there's it can have a gas exception, so you might want to write some code to handle that case. Also with a message, that messages will create, so if one contract sends a message to another contract, that other contract will basically receive a small little kind of mini context for itself. It will have a little bit of memory, a little bit of payload data, and it will return something. So one thing to keep in mind. And now, delegate calling libraries. Let's see, delegate call. So essentially what this is, it's a special type of message where you can run code from another contract, but you keep the state from your code. So instead of just calling a function and it returns what it returns, I can call a function from another contract. That code will run with the state of the calling contract. So for example, message sender, message value will be of the caller contract, not the target contract. And this concept is very powerful. And as your smart contracts become more complicated, you're going to make use of this feature often. It'll save a ton of gas. And Instead of implementing for instance, a math library on your own, you can use one that's already deployed. Now, let's move on. Logs. So logs, we touched on this in a previous video. Again, here in our coin contract, we have logs are basically the end product of us creating events and emitting events within our contracts. So, for example, here we define an event called sent. It takes in an address, from address to address, an amount, and later on, let's see where we're using it. Okay, here line 43, we're emitting that event. Now, what that means is we are now going to have a log on the blockchain of this sent event. So so-and-so sent money to so-and-so in this amount, and that will be logged on the blockchain. Now, this information is not readable by smart contracts, but it can be read from outside the blockchain. And this is possible by a special data structure called the Bloom filter that we're not going to go into here. But essentially that's a log. So logs are basically what we're doing when we're creating and emitting events. Those are creating logs that we can read later on, not via our contracts, but by other means. Now, create. Now, earlier we described a way that transactions can create contract, but that's not the only way. We have another way. So we have a special message here. I'm sorry, a special opcode called create. And basically, like it says here, the only difference between creating this and another way is that we'll actually get a return value, and it will be the address of the new contract. Now, deactivate and self-destruct. Maybe you don't want your contract on the blockchain anymore. Well, unfortunately, you can't remove it entirely. That's the point of the blockchain. Things are there and they're there forever. But there's a couple ways to deal with this. Number one is we can call self-destruct. Now what that will do is remove the state from your contract. Any money will get sent to a target address that you can specify. And that's it. That'll make the contract unusable. But there still might be some issues with it. So for example, it says here, someone can, if someone sends Ether to a contract where the self-destruct was called, and that target account to send the Ether is maybe no longer active, then, that Ether's lost. So another way we can do this is down here it describes a way you can disable it, which is basically changing your internal state where your functions revert. Basically meaning it won't accept any Ether. Even if you call the function, that function will revert and the Ether will get returned. And lastly, we have pre-compiled contracts. This is an interesting one and fun for me to think about because I actually never came across it until preparing for this video. Pre-compiled contracts, you can think of these as, they're called contracts. They're actually functions you can call, that are computationally expensive, that might cost you a lot of gas to try to implement on your own, but they're also very common enough to the point where, the people making up the EVM, they decided, hey, let's kind of bake these in. And right now there's probably 9 or 10 of them, things like hashing algorithms and cryptographic functions. And that's pretty mush it. So for example, you can call SHA-256 is the actual keyword that'll come with Solidity, and maybe we'll get into these in future sections. But this was a pretty cool thing. They behave a little differently than the rest of your functions, but we don't have to concern ourselves too much with the implementation details of how these work. But just know that there are certain handful of, I'll just call them functions because that's how we use them, that come with Solidity that are, more complicated than these opcodes, but we can still use them. Sorry, I had to cut out for a second there, but anyways, I hope that helpful. That about wraps it up. We're almost done. We still have a few more sections for the basics here, but that is the general understanding of the important pieces of the Ethereum virtual machine, and I hope it was helpful. and I hope to see you in future videos. My name is Eric, and I will work for CryptoPunks.